Okay, good morning. Welcome to Wednesday. And we'll start the session with Birgitta Whaley from Berkeley. And Brigitta will tell us about finding quantum advantage for quantum chemistry.
Okay. So thank you very much, Sophia, for the introduction, and thank you. I'd like to thank the organizers for the opportunity to speak at this meeting. And the topic of my talk will be finding quantum advantage for quantum chemistry. And for those of you that are in quantum physics, quantum chemistry has by convention been adopted by the community of electronic structure in chemistry. It's not everything in chemistry that's quantum. I fought against that for some time, but failed to change the opinion of the majority. So this is basically finding quantum advantage for electronic structure calculations in chemistry, which is a very, very important part of theoretical chemistry. And I'm going to first of all discuss what we mean by quantum advantage for electronic structure calculations, and give a little bit of the recent discussion about where to find this and what it would mean. And then I will present two algorithms, quantum algorithms that we've developed that we initially claimed empirically had quantum advantage. And then I'll show very recent work that puts those claims on a sound foundation with a computer science type of proof, showing that there is indeed an exponential gap for dequantizing those quantum algorithms. So first of all, the team. So this work is ongoing work in a collaboration with my colleague Martin Heck-Gordon, who is a real quantum chemist. He does classical calculations for electronic structure of chemical systems and brings a lot of classical expertise to our project. And on my group, which has more expertise in quantum algorithms and quantum computing, the team is here. And the work today is primarily the people involved are those in bold, and particularly I'd like to call out Oscar Leimkuhler, who's here, and whose work will focus quite prominently in what I have to say today. So this question about quantum algorithms helping quantum chemistry has become quite a hot topic. Quantum chemistry was identified fairly early, in other words, electronic structure calculations fairly early as a good use case for quantum computing. But despite a lot of activity in developing variational algorithms and also trying quantum phase estimation in the beginning for these systems, it wasn't clear initially whether there was an advantage conveyed by a quantum algorithm. And then some time ago, Brian O'Gorman, who is also a former student in my group, made a theoretical analysis of the complexity of the ground state, electronic ground state in the worst case, and showed that with co-workers that this is QMA complete, which means it's very, very hard. But this is a worst case scenario, and if you read this paper, you'll see that it's the worst case scenario was illustrated for something that didn't look like a molecule at all. More recently, Garnet Chan and co-workers, a whole consortium and several students at Caltech, examined the potential for advantage of generic chemical problems. And generic chemical problems are molecules that generally have weak correlations. I'll talk about correlations on the next slide. But these are problems that can be described by what we call a single reference state. And about 95% of all molecular problems fall into that category. So quantum chemistry is a very large field, and that the majority of problems in that field are really quite generic. And they showed empirically that there doesn't seem to be any exponential quantum advantage. And let me show you, explain how they came to that conclusion. So basically, they're comparing with the scaling of quantum phase estimation, which is shown here, which scales as a polynomial of the inverse of the overlap of the ansatz state with the true state. then a polynomial in the size of the system, and then polynomial of 1 over the precision. And if there were to be a quantum advantage, then classical methods should be with an exponential gap. Classical methods should be exponentially harder than these. So they should have a scaling which is not polynomial at all, which is super polynomial in all of these three variables. So what they showed with empirical studies is that classical heuristic methods, and these are the most famous of these in quantum chemistry, is the so-called coupled cluster, which will which will star in the rest of the talk as well. So if you aren't familiar with that, I'll show it to you soon. But what they showed is that these classical heuristic methods, which are widely used in quantum chemistry, if you want to have wave function-based calculations, these already scale in the same polynomial sense as QP here if you're dealing with a single reference ansatz. And they also showed that the same holds for simple models for correlated extended materials. However, what was unclear from their study is what happens if you have strongly correlated molecules. And we showed, basically around the same time, that somewhat empirically, that there's an exponential quantum advantage for molecular systems that possess these famous strong correlations that I'll describe in the next slide, and also strong and weak correlations. So the important thing is that you need to have strong and weak correlations together. And then subsequently, Garnett made a larger study and looked into the strongly correlated problems and realized that there really are no calculations for systems that have strong and weak correlations, which are basically these strongly correlated ab initio problems, for which you need to get accurate results. You need to converge description of both strong and weak correlation. So let me now show, for those of you that aren't familiar with electronic structure and the community, let me say a little bit about what we mean by electronic correlation and the difference between strong and weak correlation. So technically speaking, in electronic structure, we define all effects of the electrons that are not of in a multi-electron system that are not captured by a mean field approximation. All those effects are defined as electronic correlation. And the first time you encounter this, it may sound a bit weird, because even if you have a mean field system, there are, in the mean field, there is some correlation, but it's an average type of correlation. So technically, or is it just by definition in electronic structure, anything above and beyond mean field energies is due to correlation of some kind. And so that's shown schematically on the top right, where the electron sitting on the blue cloud is basically an electron in the mean field solution, which is known as the Hartree-Fock solution. And that just feels the average effect of all the other electrons. And then there's an additional term in the wave function, psi correlation, which expresses the kinds of interactions shown in the cartoon on the top, below that, where each electron is feeling instantaneously the positions and the dynamics of all the other electrons. And those are not correlations that are not captured by a mean field description. So where do we find these kinds of systems with strong correlation? Another sort of sociological thing is that in quantum chemistry, so I think it's about 1% of the energies of most generic systems, or even beyond generic systems, is due to correlation effects. So quantum chemists spend a lot of time worrying about 1% of systems that, however, which possess these strong correlations. But this 1%, however, is responsible for a very important set of chemical systems and physical systems. Basically, these systems with the strong correlations constitute high-temperature superconductors in solid state. On the molecular level, they constitute systems that have bond breaking, making chemical reactions happen. And they're particularly important for any kind of metallic catalyst, particular transition metal catalyst, where you have electrons in many, many different spin states. And then also they're involved in the ordering of electron spin states in polyradical systems. Radical systems are systems that have unpaired electrons. And if you have multiple unpaired electrons in different locations in a large complex, then you can have many different electronic spin states. And the ordering of those is quite important. I'll come back to that with a use case at the end of the talk. So these kinds of systems give rise to strong, which is also known as static correlation. And if you want to have accurate results for their energies, you have to always include the so-called weak dynamic correlation as well. Because the strong correlation basically reflects the fact that you have multiple configurations of electrons, in other words, distribution of electrons over different orbitals. So you have multiple of those necessarily. They may be quasi-degenerate, but you need to include multiple ones to get a good representation of the exact state. And all these systems show that characteristic. But if you want accurate energies as well, you have to add in the weak correlation, which is present in all systems. And these are basically very many small contributions from higher lying electronic configurations, which provide the small corrections when adding them all up together will bring the state closer to the exact state. So if you want accurate solutions for these systems with strong correlation, you have to include both types. And as Garnet said, we don't really have any methods to do this classically. So what we are proposing is that non-orthogonal quantum algorithms do provide efficient solutions for precisely this class of problems. And there's two such algorithms that we've developed over the last few years. One is the non-orthogonal quantum eigensolver NOQE, and the second one is the tensor network quantum eigensolver, which is also a non-orthogonal method. We just didn't put that in the name. So here is a summary of both of these, and then I'll go into each one a little bit in some detail before I'll deal with and give some examples, and then deal with the complexity issues. So the non-orthogonal quantum eigensolver is by construction, it's classically motivated. So we take Hartree-Fock reference states, but the point is that these Hartree-Fock reference states corresponds to different electronic configurations, and therefore they are non-orthogonal. They're represented in different atomic or molecular bases, and that's a key feature in the difficulty of these systems classically. So taking these non-orthogonal Hartree-Fock reference states basically builds in some static or strong correlation, and then we dress those states by exponential cluster correlators, which build in with the same kind of cluster correlators that are present in coupled cluster, and those build in all the weak correlations. So we have both correlations in our ansatz, and we have our ansatz is a set of these. And what I'm going to show you is that we can efficiently evaluate Hamiltonian matrix elements and overlap matrix elements of these on a quantum device. And that's the Hamiltonian matrix element, one Hamiltonian matrix element between two such reference states shown there. So we evaluate those on a quantum device. We have to repeat that many times because of shot noise, quantum shot noise. And then we classically assemble these matrix elements and solve on a classical CPU, we solve a generalized eigenvalue problem to get energies and states. So I want to emphasize at this point that because we're in the post-processing, we're solving an eigenvalue equation. The final solution is a variational solution, but it's not a variational quantum eigensolver. There's no optimization of these states on the quantum computer. The variational analysis is in the post-processing. The second algorithm is a tensor network quantum eigensolver, and this is due to Oscar. So this is also a linear combination of M ansatz states. But now these states are given by matrix product states in rotated orbital bases, and that's the analog of the non-orthogonal Hartree-Fock reference states. They are in different orbital bases. And we solve then this generalized eigenvalue problem with a slightly different method right now, but we solve it similarly on a classical CPU for the optimal coefficient C, and making measurements again of the off-diagonal matrix elements in the same way. And we have similarly variational nature of the final solution. In other words, we guarantee systematic convergence with increasing the number of unsat states n. The nice thing about the tensor network quantum eigensolver is that the circuit depth is linear in n, the size of the system. So the key features of both of these methods is that they both have polynomial scaling with the size of the system. So I'll show you that on the next slide in detail for the NOQE. And the classical analog of both of these methods are intractable. In other words, there exists no classical analog of either of these methods. There is a non-orthogonal configuration interaction method, but it's possible only for very small molecules. And if you start, well, I'll show you, I have to show you on the next slide why we can't do that for the NOQE. The closest classical methods are exponentially more expensive. And then generically, the advantage of these systems, these algorithms, is that we're using these non-orthogonal reference states, which allow for a very compact representation of a multi-reference states containing both the strong and the weak correlations. With the wave functions, basically, they're constructed with the rotated bases for the strong correlation, and the dressing describes the weak correlations. So here's a summary first of a more detailed summary of the NOQE approach. So the reason why the NOQE approach doesn't have a classical analog is that if you were to think of making coupled cluster calculations of these matrix elements between different reference states, the reason the coupled cluster works as well as it does is that in the standard form, when you conjugate the Hamiltonian by these cluster correlators e to the tau I and the same one e to the tau I dagger on the other side, that operator will truncate at exactly fourth order in the BCH expansion. And so then you can get a converged result. But if you have non-orthogonal references, that operator, the corresponding operator e to the tau h e to the tau I h e to the tau j dagger, does not truncate. And so the matrix elements don't truncate, and you basically have an infinite set. And for strongly correlated systems where these coefficients in the tau operators are large, you have a big problem. So it's computationally intractable for classical calculation to do something like the NOQE. However, if we work on a quantum computer, we're talking here about making what look like UCC type of states, which are now standard in fermionic simulation. And what the additional trick that we have is that we can calculate the matrix elements efficiently. So I'll show that on the next slide. So here I'm just summarizing the procedure. We take our fermionic operators and decompose them into Pauli strings. The Hamiltonian is expressed as the sum of the operators pi. We make use of low-rank tensor decompositions, some of which were developed here at IBM, to reduce the circuit depth, so particularly the Takagi decomposition, which Motta and co-workers developed over there. And then we can further use Trotter-Suzuki expansion to decompose the resulting exponential operators into products of unitaries. And that's described in this 2023 paper. So to measure the matrix elements, we make a modified Hadamard test, which we first proposed in what was actually a variational paper together with Bill Huggins in 2020. There's several ways to do this. This form is a way which needs a lot more qubits, but has shorter depth circuits. There's another form which has less qubits, but longer circuits. But for near-term applications, this one is better because we have shorter circuits. So we have one of our Hartree-Fock states in the top register, and then the second register in vacuum below. So we undertake the Hadamard test. We have to then, first of all, swap the UHF into, let's see. We're generating with the tau I, we're generating the reference state I, and we're swapping it down, the Hartree-Fock down into the second register, and we're generating a state J in the same basis, but then we apply a rotation on that state to put it into its own basis. And then to do the Hadamard test, we then have to rotate back. Oh, sorry. I won't take my jacket off. Is that better? Okay. Okay, so this is a little bit complicated to go through, but it's in these papers. So one has an ancilla bit that has a phase gate p theta, which will control whether or not you're measuring the real or the imaginary part of the Hamiltonian or the overlap matrix element. And what I've shown here is the circuit there shows for an overlap matrix element. If you want the Hamiltonian, you have to put Pauli operators into these circuits as well. So the ansatzes that we've looked at are, first of all, cluster operators defined by a UCD type of wave function together with MP2 amplitudes. And the idea was that MP2 amplitudes are easy to compute classically, and so everything else afterwards is going to be done by the NOQE analysis. So we don't need to have a super accurate ansatz. We don't really need to do a VQE on any of these ansatz states. And the second type of cluster operator we've looked at here is defined by a unitary couple cluster Jastrow-correlated amplitudes. And these are more efficient. You need shorter circuits, so they're a big advantage. So here's a benchmarking study in our first paper for H4, which has got 4 electrons. And it has 8 spin orbitals, so it's a very small system, but it's a very strongly correlated system, even at its equilibrium geometry. And it's routinely used as a test for strongly correlated methods. And so what you see, so in this case, there are 6 reference states corresponding to 6 unrestricted Hartree-Fock states at dissociation. And what you see on the bottom right I've shown is the energy in Hartree compared to the full CI, which is the exact energy, which can be done for this small system straightforwardly. So the black line is the exact energy, and the green dots represent the NOQE energies, which are very, very close. And this system is small enough that you can actually do non-orthogonal CI. So the red dots show the results of non-orthogonal CI, and we see immediately that the quantum NOQE, which has the additional dressing for the weak correlations, which is not present in an OCI, this is already much better. Another very nice aspect of the approach is that we can do both ground and excited states. We get excited states out from the generalized eigenvalue solutions. And the state infidelities for both ground and excited states are very high. So the infidelities are 10 to the minus 2 or less for this problem, very strongly correlated problem. So that means that we're getting very good output states. And we can, of course, we can further improve these by using a larger orbital basis set. This we're using the minimal basis here. But because we're getting such high fidelity of the states, in addition to the energies, we can use these output states into QPE should we wish to get a state with a guarantee in the hard computer science sense of the accuracy. And just to give an idea of the size for this system, we need a couple of hundred C0 gates if we're using the cluster Jastrow ansatz, which is more efficient than this one. It's about a factor of 2 more efficient. And here's a generalization. I'll just very quickly mention this. I won't go through this in detail, but basically, we started off using a real version of the cluster Jastrow. There's other variants that we've looked at more recently, an imaginary version here, or the full cluster Jastrow. And the full cluster Jastrow is very, very accurate. It just has a somewhat higher gate count. If you look on the right, you see the gate count. This shows you the advantage of the Jastrow. If we're doing UCC2 or UCCD, we'd have a gate count of 96 for this particular calculation for H2. And we're going down to 40 if we're doing generalized UCJ, and down to 20 for real or imaginary. Okay, so let me move on to this. So the resource estimates. So we calculated the gate complexity with respect to number of gates, putting all the decompositions into place. And we see that for one trotter, so K is the trotter step. So for one trotter step, K, then the scaling goes quadratic with the size of the system in terms of spin orbitals, and is linear in the decomposition threshold of the Takagi decomposition, which is less than or equal to n squared. So n squared, of course, you just have the n to the 4 scaling. It's normal with coupled cluster, with unitary coupled cluster. But our experiments show, or our tests show, that we can set L essentially to 1 or 2. So we basically have a low polynomial. And if we compare this with the classical analogs, well, as I mentioned before, the classical NOCI-CC is intractable, so it doesn't exist. Classical NOCI-MP2 does exist. That's truncated, and it's been tried by Martin Head-Gordon's group. But this is non-variational, which is not a good thing for quantum chemistry. And just comparing classical coupled cluster, you'd have n to the 4 plus, and then if you want unpaired sites for these strongly correlated systems, you'd now have another factor of n to the d. So there's an algorithmic quantum advantage for NOQE. There's also a practical quantum advantage here, because NOQE is both variational and size consistent. And that's something that quantum chemists care about a lot, particularly when you have bond breaking. You want to make sure that your method can describe the energies going from something which is strongly bound to something where you have two fragments and are no longer talking to each other. So that's known as size consistency. And basically, only Hartree-Fock and full CI are both variational and size consistent. So this is an important practical advantage. So now let me go to the tensor network summary. This is Oscar's work. So the reference states here are matrix product states of fixed bond dimension, shown there, where we represent, shown here as the equation. And then below that, we see here that, so the matrix, if you put the matrix product state in the usual form of representing it with bubbles and lines, put it on its side for the state phi I on the left of this circuit diagram. And then you have a circuit of orbital rotations, which are, I'll say more on the next couple of slides about these. These boxes represent orbital rotations known as Givens rotations, which are two spin, 15, okay. Two particle rotations, two qubit operators. And then one goes to a different matrix product state on the other side. This circuit would compute the overlap matrix elements. And if we had a Hamiltonian matrix element, we'd have to insert a row of Pauli operators after, say, Gij. So this is the tensor network quantum circuit, which evaluates the matrix elements of the Hamiltonian and the overlap matrix on a CPU, essentially by the same kind of Hadamard test that I showed before. So you see, in this case, the ancilla qubit is on the top. It's put into the Hadamard basis, and then you have a set of, so you start off with everything in 0. You have a set of unitaries, controlled unitaries, which prepare the MPS state, and that's linear in n. Then you have this array in red of the rotation matrices, which transform you from one basis to another. And then I've put here the P alpha, the orange, the Pauli terms from the Hamiltonian. So this picture represents from Hamiltonian matrix element, the circuit. And then UJ dagger is the corresponding preparation for the state on the right. So the overall gate count here is also goes n squared plus n times the bond dimension of the MPS, which we want to keep small. And the circuit depth, as I mentioned before, is linear, which is a big advantage here. So this is solved on the CPU. The generalized eigenvalue solver is solved on CPU, and there's various ways you can do this. It's basically a quantum subspace diagonalization, just as in the NOQE. So in the first paper, Oscar's paper, we used the generalized sweep algorithm, which is an extension of classical DMRG applied to the TNQE. That has a much higher measurement cost than NOQE due to the sweep algorithm, but it's not. But this can be improved, and we're working on that. So I'll just show you this one example here, which shows, just to show so I won't go through all these numbers here, but this is a comparison of a TNQE calculation with a single UCCSD. This is actually the only variational calculation in the talk. The UCCSD is a variational calculation with one reference state of the energies for octahedral H6. Octahedral H6 is even more strongly correlated than square H4. We actually had to search a lot to see if there's any precedent in the literature for calculating octahedral H6, but as you can imagine, it's highly strained. And so what I want to show you is that if you run TNQE, you get 99.7% of the correlation energy, whereas if you optimize as much as you can a single reference UCCSD, you only get 33%. So it's a significant improvement there. And the other thing to point out here is that the number of shots is it's a lot less than the variational UCCSD, but it's still pretty high at 6.4 times 10 to the 16. That is higher cost. The high cost is due to the iterative nature of our subspace diagonalization in this case. Okay, so here's a summary of the features. And now I want to move to, in the last 10 minutes, to the complexity theoretic analysis. So this is very recent work of Oscar. I had a poster on it yesterday afternoon, but some of you may have seen that. Basically, the message of that work is that these low-depth quantum chemistry circuits, which describe specifically this category of systems with both strong and weak correlation, they are provably hard to simulate by any efficient classical algorithm in the worst case, assuming that the polynomial hierarchy doesn't collapse. In other words, one can come up with algorithms that do, but they will cause the polynomial hierarchy to collapse. So I think we generally agree that polynomial hierarchy shouldn't have collapsed. So let me tell you a little bit about that. So this starts really here, which looks like something very different, but it starts with a theorem that Oscar proved about orbital rotation circuits. I've said before that these orbital rotations between these different reference states are very, very important. And here you see exactly why they're important. So if one constructs a family of orbital rotation circuits, and that's shown in the middle here, the red box, shows basically this is the gadget representing some set of orbital rotations represented by Gibbons rotations in the G's, and then some fermionic swap gates next to them to put things together. And so if you have this orbital rotation circuit together with input states supplemented by what's called a fermionic magic state, which looks something like this. It's a 4-cubic state that looks like 4 Slater determinants, if you like. Then under post-selection, so that's shown on the right, you can make 2-cubic gates, CD gates. So with that, you have basically a universal gate set. And so this is then universal for this family of circuits is universal for quantum computation under post-selection. Now this has two corollaries. Firstly, if you want to exactly compute the output probabilities of such circuits, that's gap p hard, which is a complexity class sort of the same order as NP hard. It means you have to count plus and minus outputs, which classically is very, very hard. And secondly, classical sampling is intractable also under the generalized P versus NP conjecture. So I think I'll skip this. This is just examples of match gates for people who aren't familiar with these. This is the particular form of a match gate G. And so examples of these are the fermionic swap gate, the Gibbons rotation gate on the top, and the phase rotation gate on the bottom. So the implications of this for quantum chemistry are that if we have these multi-reference methods that we've talked about, if we wanted to exactly or compute, or even to some multiplicative approximately compute the overlaps for the entangled reference states and reference orbitals, this is gap p hard by corollary 1. Secondly, if we were to look at some way of getting an additive error by dequantizing using mid-circuit sampling in a computation basis, that's also ruled out by those two corollaries. So in other words, there's no way that we can think of that there's no way to dequantize these calculations of the off-diagonal matrix elements of the Hamiltonian and the overlap. Another result here, which is quite interesting, was almost hiding in plain sight, is that the generalized UCCSD states, actually the circuits generating those are universal for quantum computation. And importantly, they can encode universal quantum computation with polynomial overhead. And that follows from a result of Arad and Landau. So for the non-orthogonal quantum eigensolver here. Okay, so yeah, so I just summarized a little bit in detail how this works for the non-orthogonal quantum eigensolver, but I want to come to this summary at the bottom in red, which is basically the statement that now we have provable guarantees that there are exponential quantum speedups for two choices of reference states that include both static and dynamic correlations to model the electronic eigenstates of molecular systems. So in other words, these linear, the important thing is to remember to take home is these are linear combinations of orbital rotated matrix product states. Those are preparable in linear depth. Or we have linear combinations of generalized unitary coupled cluster with singles and doubles. So when we compute the matrix elements, the off-diagonal matrix elements between those linear combinations, we will have precisely those off-diagonal matrix elements that I showed you that the circuit's for. So one last point, caveat, you may worry about this. So these results are worst-case complexity results for systems for this class of systems. Of course, we want to extend this to average case complexity. Because remember in the very beginning, I told you there's a proof that electronic structure is QMA complete, but the actual instance that was used to show that didn't look like a molecule at all. So it may be, so here are two hypothetical scenarios for subsets of the state space, which are spanned by a particular class of ansatz states. So it could be that the hard instance, on the left-hand side, is a situation where the hard instances of that set of ansatz states are in one group up the top, but the useful instances, or the useful states from that, are somewhere else in the space. And there's no overlap between those. So that wouldn't be a good situation. More useful situation would be if the hard instances are basically covering most of the class of ansatz states, and this, which is expressed by the statement that the states spanned by the ansatz class psi, the whole circuit, are average case hard, which means that more or less everything in there, if you do hard random sampling, more or less everything is in this hard category. Now, this is really where we want to be. We don't have a rigorous proof of this, but there's very strong evidence that this is indeed the case here because of results by a group in Poland, Osmaniak et al., who were studying fermionic linear optics, which is basically nothing other than quantum chemistry in disguise, but they were coming from the boson sampling literature, and so they then changed the bosons to fermions, and the beam splitters become basically basis rotations, and so we have basically a very similarity. So they showed that there's a worst to average case reduction. They didn't have the worst case, so actually our worst case complements their results, but they did show they had rigorous results for the reduction of the worst to the average case. And the reduction is from whatever the worst case is to p-sharp hardness for both exact precision or for an exponentially small additive error. For precisely these circuits that we've been studying, which are the particle number preserving match gate circuits with magic states inputs. So this provides very strong suggestive evidence that our results actually will apply for the average case, and they aren't just worst case. So I think, how much? 2 minutes. Okay, so this is okay, so let me focus now on a second issue. Or make a couple of comments about a second issue, which is the cost of measurement in this algorithm. So clearly we have to make many repeats of these circuits to estimate the Hamiltonian matrix elements and the overlap matrix elements in order to generate the inputs for the classical post-processing. And so we looked at the measurement costs of the Hadamard and compared this with doing shadow tomography. So we extended shadow tomography methods to evaluate these off-diagonal matrix elements. And here, a very interesting result came out. So initially, we were looking at small qubits. For small qubits on the right here, you see that the shadow tomography is more efficient, and it's better for high precision. But if we increase the number of qubits, then we come to the situation on the right. With 20 qubits, we're basically very quickly being in a region where the sorry, the blue. Oh, it's the other way around. Yes, other way around. Sorry. on the left is if we have 20 qubits, which is still relatively small. And here, the blue is the shadow-based. It's more efficient here as we increase the number of reference states. But if we go to larger number of qubits, shown on the right panel there, for a given number of reference states, as the number of qubits increases beyond about 30, the NOQE, the original Hadamard test, is more efficient. So for going forward, we're going to have to stick right now with the Hadamard test, although we're looking at other methods. And this will be my last slide, which is when can we use this, or how soon can we use this for something useful? And so motivated by the massive speed up in the rate of production of hardware, we did some thinking about systems, what we could do with 100 fault-tolerant logical qubits, which is on the radar for the 2029 machine of Quantinuum. And we realized that in photosynthesis, there's this photosynthesis, I work a lot in photosynthesis. This is one of my pet projects here. This is a cluster which is responsible for splitting water and generating H+ and electrons, which are then used to actually make the chemical reactions of photosynthesis. And what we realized was that we could do a nearly full valence electron calculation for this core metal oxygen cluster with about 100 logical qubits. We can encode this in a near-term version of high-rate fault-tolerant error-detecting codes. And this particular one is from Goto. It's a hypercube code that only requires about 200 physical qubits. So here comes a big advantage of our methods. The ansatz preparation circuits require only about 10 to the 6 CNOT gates for fault-tolerant level 1 preparation. So we expect this is possible in the next 5 years, plus or minus, using the post-selection and error mitigation, which is the current modus operandi, certainly at Quantinuum. So with that, let me close. Actually, let me just leave you with this here, which has the references. Thank you very much.
Maybe the next speaker can come, and we have time for one quick question. Ryan?
So I'm pretty interested in this sort of evidence for average case hardness I'm interested in this evidence for average